Hi everyone. Thank you so much for joining us today. Today we have Lucas with us, who, if you are into computer vision, he does not need any introduction, but I'll try to introduce him. So he's a senior staff researcher at Google DeepMind and author of some very impactful work such as Vision Transformers. He has his PhD in robotics and computer vision. So I'll just hand it over to him. Thank you so much.
Yeah, thank you. I was unsure what we do with the timing. The calendar event is for 1 hour. Is this like a 1 hour talk with questions throughout, or we do half an hour talk?
Yeah, as you're comfortable, no problem.
Okay, but we have a full hour and can
Yeah,
split it anyway, right?
yeah,
Okay, yeah,
yeah.
then let's do people can ask questions throughout. And if at some point we get stuck too long on one slide, then I just say, okay, no more questions here, let's move on. And I'll keep track of the time. Also, yeah, so thanks for the introduction. I will present Siglip, but I actually want to present a little bit more surrounding context. And I like this title slide. We used it for ICCV, which was in Paris. That's the only reason there are the two Eiffel Towers, and I didn't edit. So yeah, Shawa is actually here at the office, but not with me. These are the authors of the Siglip paper. Um, what is this? AI assistant. Okay. Then let's get started. So as I said, I want to give a little bit broader context before diving straight into the technical details of Siglip. And my first few slides, some of you who have seen talks from me before may be familiar with them, but I still want to present them to get everybody on the same starting place. So the main goal of me and various people in my group, and I think a lot of computer vision researchers in general actually, is to somehow get a model that is a good general visual representation. And why we want this is because we believe that this is necessary for building models or machines or robots or whatever that can actually perform meaningful tasks in the real world. For example, for me concretely, I want that at latest at the end of my career, there exists a robot that any non-technical person can teach to do any task. And I believe that really good and robust and generalizable visual understanding of the surroundings is one of the requirements of it, not the only one. So I work towards that. Now, what does it mean concretely? So this is my favorite slide that I've used a million times, but I'll use it again. Let's play a little game together, and that will show you very clearly, I think, what I mean by a general visual understanding. So I show you these pictures. I say these are class A, these are class B, and these are class C. And then I show you a new one. And just in your mind, is it class A, B, or C? And I can probably already stop, and you probably all made up your mind. Yeah, this is class A. Another one of things that are maybe a little less common in your life, but you may still have seen a few times. Class A, class B, and class C. And then I show you a new one. And this may be a little bit harder than the previous one, but I'm sure you all got by now that this is class B, very likely, right? The basketball field as a satellite image. And then maybe quite a lot harder, depending on whether you've seen this data set before or not. And probably some of you may have never seen this image type in your life. Class A and class B. And I show a new one. And this one may need you to think a little bit more and wonder a little bit more. But I think usually by now, let's say 80% of the people usually got it right, that this is class A. It's like 3 objects, no matter what. And class B was 5 objects, no matter what. So this is what I mean by a general visual understanding. You come equipped with it. However you got it, I don't really care, but you have it. Like I show you a few pictures of new things that I can group in different ways, or I can describe to you, this is blah, this is blah, this is blah. And you quickly get it without me having to explain much, just showing a few cases. And then you quickly generalize to new images of this and make a reasonable guess on new images, right? So this is really the goal. And then some time ago, with our colleagues a few years ago, we set out to tackle this. And the first thing we need to do to tackle something is to measure how far we are from that. And then we designed a benchmark for this, which we call the Visual Task Adaptation Benchmark. If you are more of an NLP person, it is very similar to Glue, and it was around the same time, actually. So basically, we say you pre-train or do whatever to come up with your model that is supposed to have this general visual representation. Then there is this abstract landscape of all visual tasks that make sense, like not complete noise as a task, for example, but something meaningful. And we sample from this landscape of all, let's say, almost infinite tasks that make sense. We sample a bunch of them. So in this case, we basically, what this means is we got 19 concrete but very diverse visual tasks. Each of them come with a very small training set, just like in the game we played, and a test set. And yeah, we tried to cover a very broad diversity of tasks. And then your model, your general visual representation, you have the chance to adapt it on this small training set of each task and then test it on the test set. And then you get a score, and we just take the average of all of these, and this is the VTAF score. And the assumption or hypothesis is by pushing this average number up, we get more and more general visual representation. And typically in practice, this is done by pre-training in some way, like supervised, self-supervised, whatever, and then fine-tuning or transferring with adapters to each of these tasks. But we don't prescribe exactly how this should be done. Yeah, these things have many words like upstream or pre-training, transfer, downstream, fine-tuning, and so on. Now, this is the setting and the ultimate goal that we have. And then we spend a couple years trying different approaches how to get there. And I don't want to say too many details, but basically the one that worked best and most efficiently also is just large-scale supervised pre-training. In that case, let's not talk through all of these graphs. The bottom line is that we had internally available a huge data set, which was called JFT, and had back then 300 million images. And there were a few public data sets like ImageNet, 1 million images, and another variant that was much less known, but full ImageNet in quotes, that was 14 million images. And back now, I think everybody just agrees, and that's good. Back then, what we figured out is that if you pre-train a large model on the large data set for a very long time, these three things together, then you get a really good model or a really good, really general visual representation if you want. So on our Vita benchmark, this topped everything, and we did try a lot of other approaches before, like self-supervised, semi-supervised, all kind of things, generative models too. And when you do these three things, basically you get benefits everywhere. You get much more robust also on typical robustness benchmarks. You get much better at quickly recognizing new things, like these few shot examples we had before, but also much better at fine-tuning on large data sets. Like basically you get wins across the board. Okay, but this has one issue. Let's see what's next. Yeah, this has one issue is that you actually need this large labeled data set, right? This was 300 million images labeled by, if I remember correctly, about 30,000 class labels, and is Google internal, and there's no way we publish this. And so really nobody can use this. And I think even a couple years after we published this, nobody has had any data set like that, or at least reported about it in any papers. So in that sense, it's a nice proof of existence in the sense that we showed, look, if you can manage to have this, you can get great results. But then practically speaking, it's not that useful to the rest of the world because the rest of the world doesn't have such data. And it seemed that over the course of a couple of years, um, nobody stepped up to build such a data in the public for the public, which is reasonable because it is quite expensive to get that and a ton of work, right? Um, but then something really cool happened, really cool in two ways. Is that language became an API for vision. What do I mean by this? Basically, clip and align happened. And I believe most of you know clip, but I still want to explain it to set the stage for SIGLIP. So clip and align are essentially the same thing at essentially the same time by OpenAI and by Google. But clip is much more popular because they open sourced models and Google didn't. But what does it do? It basically changes the pre-training from this large set of labeled images to a large set of, let's say, not explicitly labeled images, but just of image text pairs that you can get in whatever way that may be much, much less expensive than requiring humans to hand label a predefined set of classes. For instance, I think in Clip, they didn't say exactly how they got them, but in Align paper, they said, for example, that they use images on the web and the alt text tag that comes with it. You know, when you have in a web page, you include an image, it's this img tag, and then source is the path to the image, and then you can have an alt equal, and then some string, which is supposed for accessibility for screen readers and things like that, but also search engines to understand the content of the image without needing computer vision. And so this is nice. Like this is a text that is supposed to describe exactly what is there in the image. Vast majority of images on the web don't have that, but significant amounts still do. And so both of these models figure out a way to pre-train on that instead of in a classification way on label data. And then this has not only the benefit of having much easier or more readily available data, but also it has a huge effect on how to use the model, which I think is really cool. Basically, now you can use this model, and I'm going to explain in great detail how next, but use this model to transfer it to all kinds of tasks without needing any small data set on the task to fine-tune on, and without doing any fine-tuning or any training in any way, by just really spelling out the class names, and that's it. So yeah, this is, I think, two great things that came out of Clip / Align. And just to exemplify the change in the pre-training data, right? Previously, all data sets in Vision basically that have anything to do with pre-training were something along that line, like a set of classes that somebody comes up with, be it engineer at the company or PhD student in their lab, but somebody comes up with the set of classes, the concepts they want the model to learn, and then collects a list of images for each of these classes. Versus what Clip and Align can train on is just random image text pairs from the internet, which can be much, much worse, like this one. This is just crap, image and thumbnail for version, blah, blah, blah. It doesn't say anything about the image. Or it can be quite precise, like here, motorcycle front wheel, right? Or this Frankfurt airport skyline, and then the date, okay, I don't know. But these are things that are more detailed than any classes anybody would come up with when they just think about the list of classes to come up with, right? So you can see that if we are able to leverage this kind of data, our models could actually understand a lot more. Then the question is just how to leverage it. And then basically what Clip and Align, both of them do, is this. You have this mini batch of image and text pairs, right? Here you have this image and the text that goes with it, both on a mountain lake with lighthouse, right? And here we have 3 of them. Then the images, you all send them through an image model that takes in an image, outputs a single vector. Let's say 512 dimensional vector for each image. Similar with the text, you send it through the text encoder, each of the texts separately, and for each text you get a vector of also the same, say 512 dimensions. And now how you train this is simply you say in the loss, I want the image and text, the vectors of the image and text that belong to each other to be more similar than the vector of image and text that do not belong to each other. Um, and that's how you train it. And we'll go through even more detail on that point pretty soon. And then when you train the model in this way, you can later use it in a very nice way. Like if you have a new task, you basically describe the things you want to recognize by writing down the text. Let's go back to the example we had in the beginning, these flowers, these three classes. Now I don't call them ABC, but I actually write a picture of a pink primrose, a picture of a pocket orchid, and a picture of a daisy. And notice I don't need any images for this. I just define my task by writing it down. Send these strings to the text encoder and get my three text vector embeddings. And these are now the embeddings are representative for this class of the thing that I want to detect or to recognize. And now I give you this new image that you have never seen before. You send it through the image encoder and get the corresponding image vector. And now you can just compare this image vector to each of the three text vectors that we got, and you get a score for each one. And this is basically your score, that the image actually, or how well the image matches each of these texts. And then if you want to choose one, you can just take the max, or you can take the softmax if you want probabilities, and then take the highest one. That's basically how you then use this, or how you can build a classifier without even needing images to build it, right? So far, so good. Okay, no questions? Then maybe this was all perfectly known to you all, then I apologize for the time. Yeah, okay. Of course, you may also know it's not always just that simple. Like you need to nicely decorate these texts, and there is like a whole prompt engineering that goes into it. Like it's better to write a picture of or a flower called pink primrose than just pink primrose. But hopefully, this is something we'll get over at some point as a community. Now, that's the cool thing, right? In this setting that I presented before, basically this whole step of adapting and needing the training set per task, it just goes away. And we just write down what we want as the new task. Okay, so that was clip. And I think somebody wrote a question. Let me see if I can read it. So the question is, so naively, in a way, clip is learning search rankings, since data is curated from search by respective text descriptions. The training data is not related to search. This is how people classically used to build the data sets, right? Like maybe ImageNet, CIFAR, and so on. They came up with the list of classes and then enter these classes in some image search engine and then just take the images that they find and say, okay, these are my classes. I think this is the process behind at least CIFAR and ImageNet. And then maybe some sanity check human raters. But in this case, for clip and align, there is no such thing because nobody came up with a list of things to search for in the first place, right? There's just somehow, maybe by starting from some seed thing like command crawl or something like that, get a large amount of image text pairs from the web. Related question. Would it help to pose it as a list-wise ranking problem with a Colbert-like alignment module instead of basic contrastive loss? I actually don't know what is Colbert-like alignment module, but the softmax classification that Clip does. So Clip, actually, let's go there now. I think this is even my next slide. Let's see. Yeah. So here a little bit more in detail, the loss that Clip does is bidirectional softmax. So for this text embedding, compare it to all the image embedding and ask for the corresponding one to be higher rated than all others, or specifically take dot product of this text embedding with all image embeddings, take the softmax, and say ground truth label for the correct one is 1 and for all others is 0. So kind of a classification task. And I believe, let's say I'm 90% sure, I believe by optimizing this classification task, you are at the same time implicitly optimizing a ranking task. And the thing is, this is just one direction and there is an asymmetry. So clip loss also does it in the other direction, like this image embedding, compare it against all the text embeddings. Again, take softmax and request for the correct one to be the class basically, or class 1, and then all others to be zeros. Oh, there was clarification, late interaction on the token embeddings instead of a single vector to vector. Yeah, basically, if you do anything on top of these embeddings, image and text embeddings, as opposed to them just being vectors and doing dot product, if you put some other neural net module on any pairs of them, it makes everything to do in the future more expensive. If you want to do something like retrieval, right? Let's say you want to build a retriever, image retriever. You can have your huge database of, I don't know, 100 million images, embed them all and store these embeddings in a database. And then any user comes, asks for a text, you embed the text, and then you can quickly compare it by doing dot product with all of the images, and then retrieve the most relevant images that way, right? You could try to learn a small neural net module or anything on top of pairs of embedding, for example, or even more to get slightly more precise rankings or something. But then if at retrieval time, you need to run all pairs through that, for example. So it gets more expensive. You can probably perform a bit better. The trade-off. All right, so this is what Clip does. And I mentioned a couple disadvantages of this, actually. One that I just mentioned, it's bidirectional. We need to take the softmax both ways. The next thing is that this training, a clip and align, is usually done with a quite large batch size. The clip paper had 32,000 batch size across 700 or 800 GPUs, I don't remember. And the align, I don't remember the specifics, but they also had something large, like similarly large batch size and probably TPU devices. And then in the softmax, you have the normalization, right? So you need to sum across the whole rows in order to just be able to normalize, and the whole columns again. So you have these global sums going on to compute the softmax. That is yet another disadvantage. And then it just intuitively feels like a maybe weird learning task, although I guess it depends on your taste. Like as I mentioned, this is basically in the direction from image to text. It is kind of an image classification task with a list of classes that is made up on the fly, defined by what texts appear in the mini batch. So it changes all the time for each mini batch. And at the same time, the classification task the other way around. For each text, classify by the classes being defined by the images that appear in the mini batch. I think it can be argued whether this is like a nice magically regularizing thing, or whether this just, to me, this just feels arbitrary and wrong. But yeah, that's why I have a question mark. I think it's a matter of opinion or of results in the end. The main disadvantages being the first two, that it's bidirectional, so you need to compute the softmax twice and these global sums, which at a small single device setting, a small batch, maybe 128, it seems a bit overblown. But as you scale this up to batch size, let's say 32,000, for example, which is the default, then actually this matrix here and the operations on it make up the vast majority of your memory usage, more than the model even sometimes, and of your time. So that's why we started digging into this and figuring out, is this really needed, or are there other ways that are simpler, more scalable, maybe. And that's how we got to Siglip, which in hindsight is super simple, which is just saying, okay, then change this from a softmax-based loss to a sigmoid-based loss. Meaning, instead of doing this kind of classification across the other modality, just take each image and text pair, like each entry in this similarity matrix individually, and look at it in isolation. Like this pair, this image here with this text here, this one. Do they match? Yes or no? And that's your task, your loss for this entry. Same for this one. Do they match? Yes or no? And that's your task, the loss for this entry. So there needs to be no global normalization, no, you don't even need this whole matrix to exist at once, which you do if you want to do the global normalization. And there is no bidirectionality needed, right? It's just each entry in this matrix, yes or no, do they match? So this, we found it works a little bit better, but especially it scales a lot better and requires much less memory and less compute on the loss. And this, because it's basically clip, but just exchanging the softmax with a sigmoid, so we call it siglip. Then, yeah, okay. Just want to show that also algorithm-wise, it's or code-wise, it's actually super simple. If you take the pseudocode from clip and turn it into siglip, it's really just changing to log sigmoid loss as opposed to softmax. I think the code is even shorter than the pseudocode in clip because it doesn't have bidirectional, but you need to add a bias here. And this we will talk a bit more about it later, will we? Yeah, maybe. Now, one thing that we can do to make it even more efficient and to make things even more scalable, that now becomes very simple with Sigmoid because we don't have a global normalization sum to take care of that we would have in Softmax, is what we call the chunked sigmoid loss. And it's the following. Let's say you have 3 devices and a batch size of 12. So on each device could be a GPU or a TPU, doesn't really matter. On each device, we have 4 images and their corresponding texts, right? And this is the global view of this similarity matrix. In reality, we want to compute the loss on each of these entries. And that is then the global loss. So the naive and super inefficient way to do this, but the way that is the most obvious when you do softmax, is to just gather all entries from all devices onto one, and then there do the softmax computation, do the loss, and then the sum. However, once we realize that in the sigmoid case, each entry, the loss of each entry in this matrix is completely independent, we can come up with a much nicer algorithm to compute this. Basically, first step, each device just computes it on the entries available on itself. So there is no communication needed. We compute the loss on this subset for this device and on this subset for this device and on this subset for this device, right? Then, and this is a little bit hard to illustrate, we tried our best in this picture by moving the device here, but in reality, then like shift the texts, like give your text embeddings to the device left of you. And each device does that, right? This is little communication, but then we end up in the state like here. Now device 1 has texts 5, 6, 7, 8, which previously device 2 had, and so on. And so each device now sees, without even shifting the image embeddings, now sees a different part of this matrix and can compute the loss on that part, or chunk instead of part. That's why we called it chunked. And then again, move the text to the device left of you, and then compute the loss on the next chunk. And always accumulate the loss in the same buffer, because at the end of the day, when we have the loss of all entries, we need the global sum of everything, but we can do this by just keep accumulating. Yeah, and that's it. And that way we can, basically the whole contrastive loss does not take up any considerable amount of memory from our device anymore. which was the major thing holding back scaling up clip-like models before. There was always this intuition that for contrastive models, since your most, let's go back, most examples on the mini batch are really trivial, right? Here, let's say these three examples. If one of the texts just has the word dog in it, like it's a no-brainer to figure out which of the images has that. But so in the initial phase of learning, maybe that's good. It's not too difficult. But as the model has learned some very simple trivialities, then it would be better to have much more difficult cases in the mini batch, right? Like maybe let's say 4 or 5 different breeds of dog in the same mini batch, such that the model has to differentiate them. Because let's say the example that throughout the training in your mini batch, you always just see one picture of a dog, maybe different breeds. But the text is always the breed of the dog. It's a bad example because I don't know dog breeds off the top of my head, but you can think of some. Right? Then the model would actually just learn to associate these different dog breeds that it saw in the text, but just to the concept of dog. There is no reason to differentiate them if in a mini batch there was always just one dog visible. And so it would learn the concept of dog and the names of dog breeds that exist, but not actually to differentiate those dog breeds. That's why it has always been the aim and the intuition of people that any kind of contrastive learning, we need to scale up the batch size to get more difficult examples in there or hard negatives in there, such that the model learns more fine-grained nuance. And so with this change, we can now actually test this hypothesis, because now the size of this matrix, the batch size, does not really influence our memory usage anymore. We can scale to almost arbitrary batch size by using this chunked sigmoid implementation. And so we did that. And that was actually the main aim of the project. We wanted to scale to outrageously large batch size and see how much better do clip models get by doing that. And so we did that, increasing batch size more and more and more and more. Do I have this? Yeah. So we have 2 different settings. I will say a bit more about this later, but we went basically up to a batch size of 1 million. And then what we found is that in both settings, left and right, it seems that actually batch size around 32,000 is close to the best. And beyond that, much larger batch size doesn't really give you that much benefit anymore, at least according to the few metrics that we actively track, like ImageNet zero-shot classification, Cohere retrieval, and things like that. So that was one learning from this. Throughout the other thing that you can see here is that between using sigmoid loss and softmax loss, throughout the training, almost throughout the training, sigmoid loss performs a bit better than softmax loss. And the nice thing is, going to smaller batch sizes, the difference gets larger. So basically, if you cannot use large batch size, maybe because you don't have many devices at the same time, then sigmoid is definitely a better loss to use than softmax. Then, okay, there is maybe a negative result ish. One thing we were hoping. Oh, wait. A question about hard negative mining. Yeah, I will come to that towards the end. Maybe one negative result is that we also in our group really try to have multilingual models and to push them as far as we can. If I will have a slide on that later, but basically, I think the original clip and almost all published clip models are usually trained on English-only subsets of data and perform well really only on English. The reason is, if you train on multilingual data, the way I described to you how we can train models on just data from the web now, right, without needing to predefine lists of tasks and so on, this originally just sounds great. Yeah, we can get data from the whole web, which means in all languages, and we can easily just for free have models that perform well in all languages, right? But somehow people don't do this and stick to English, training English clip models, um, including ourselves. But some of us always push to train on multilingual and evaluate in multilingual ways. But the models trained on multilingual data are always behind those on English data on the standard benchmarks. Of course, if you evaluate a multilingual model on, let's say, a French benchmark and the English only model on a French benchmark, then of course English only will be crap. But on the standard benchmarks, which are mostly English, like ImageNet, Coco Captions, and so on, the multilingual is worse than the English one. And we had one hypothesis that if we can scale up the batch size a lot, maybe this will help the multilingual model to catch up. Because if you have a fixed batch size of 32,000 examples, and you have, I'm explaining the intuition now, and you have only English text and images in there, okay, like there is no easy shortcut, you need to match them. But let's say you have a mixture of languages and images in there. Let's say still a lot of English images, but also a bunch of Chinese images and texts. Then there could be a shortcut, right? That the model matches Chinese characters with, let's say, Chinese looking images of maybe typical Chinese looking images, images of cities or traditional things or people even, right? At least there could be a shortcut that makes the effective batch to be actually two smaller batches, the English one and the Chinese one, because it's just trivial to separate them. And so that's why we thought, yeah, maybe scaling up the batch size a lot will make the model on multilingual a lot better. Unfortunately, that turns out not to be the case, which this plot shows. It's the same, like around 32,000, it hits the peak accuracy, and then it kind of goes down a bit. So we were quite disappointed by this result. All right. Yeah, this is a huge table, but it's basically to say across all model sizes, like base and the different sequence length or slash resolutions, and large model, we train SIGLIP models that are the best by far. So for example, here, like original clip from OpenAI, 76% ImageNet validation, and we also have Coco numbers. But basically, SIGLIP is much better than any other models across the sizes, and we actually were able to open source all of these SIGLIP models. So they are just available, you can download them and use them. And we also trained a larger model. This SO 400 million is a size or a shape of vision transformer that we developed in a separate paper where we looked at if scaling laws can be used to predict optimal shapes of transformers. Shape mean more detailed size, not just number of parameters, but number of layers, model dimension, and MLP dimension. So this is much smaller than the G or H or even E models, but actually we trained the clip model of that shape that performs better than even these larger ones. So big table, many numbers, just to say if you need the image text model that is really good, just download and try out SIGLIP. And we don't just look at benchmarks. So we also looked at a bunch of difficult pictures that we just came up with. The first ones are on the internet, so we cannot be sure that the model has never seen them. They are not part of standard benchmarks, but they are just on the internet, so the model may have seen them. This one is quite famous from a long time ago, an OpenAI blog post about fooling models, but it actually works pretty well. If you can see here the texts. And keep in mind, in usual demos that you see of contrastive image text models, the score given to an image text pair depends on the others that are there, because people usually take the softmax, right? But here for SIGLIP, this is just individual pairwise scores, right? So this 100% of match between this image and the text, an apple with a note saying iPod, is completely independent from all other texts that are there. Right, so basically it works quite well on difficult examples, or here like cold drink on a hot day versus hot drink on a cold day. It also works quite well. This is also in, if you just search for it on GitHub, there is a collab. This table is just a straight screenshot from a collab that we published that you can also play around with and just run and try out different ones. And then the images to the right are images from ourselves that definitely were never on the internet even before. And it still works really well on them. I'm not saying OpenAI Clip would not work well on them. It probably also works reasonably well on them, but this was our kind of sanity check that it also works on never ever before seen things. And it can also reasonably well like understand the text in the image. Like here we held the science siglip, and just if we write a photo of the siglip authors, it like is very happy about it. And here, this one is interesting also. Me and the colleague Basil wore t-shirts that both had to do with coffee. Mine says, the text there says something like current mood need coffee or something like that. And Basil's is the molecule of caffeine. And I think it says the text caffeine. And then it just fires really, really strongly on the text a photo of two guys in need of caffeine and not at all in need of water. Also, one thing in general with these kinds of models, the more precise your text is, the higher you get the matching score. If you are just very vague with very vague with the text, then it gives a reasonably small score. Like here is an example, just the word cow, no prompt, no a picture of, no nothing. And then it just gives like 35-ish% to these two pictures, right? But if you are much more precise, like a cow in a tuxedo, boom, almost 100% for this one. And almost 0% for this one because it has no tuxedo. So this is just like a general thing to know when working with this kind of models. Okay. Then also want to say again what I said previously about multilinguality. I think this is the first clip like image text model that has been open source that is pretty good at multilinguality. We also have a second collab linked somewhere in the GitHub or in the first collab, I don't remember, that tests this. And we tried to test like some kind of cultural things. I think most of them you would only know if you're Chinese, but ants climbing a tree is also, if you literally translate it to Chinese, which I cannot, but is these two texts, is actually the name of a dish. Which if you write it in English, like a person in English wouldn't know what do you mean by ants climbing a tree, so it only fires on this, not on the dish. But then if you write it in Chinese, it totally knows what you're talking about, so it fires on the dish and not on the literal ants climbing on a tree. If you have more examples of this thing in your mind, please shoot us an email with these examples. So we're actually looking for them to investigate more. How many languages was it trained on or supports? Hard to say. In the training set, there are more than 100 languages. I think it's the maybe not exact same, but very similar data set as the Pali paper. In the first Pali paper, we give some statistics, and I think we said has more than 100 detected languages. It doesn't mean it's equally good on all of them, right? The more rare languages, it should be worse, I would expect. But basically, try any language and see. There is a good chance it understands, at least to a reasonable degree, a language that you think of. Actually, I should ask my Swiss colleagues to try Swiss German too. And definitely, especially for multilingual / multicultural aspect, just shoot us an email or a tweet or whatever about your experience. We're especially curious about that, actually. And given we don't cover all the cultures among our colleagues, we also cannot understand or think of all the different ideas how to test it or ways how to test it, right? All right. Another thing that happened a bit after that is you may have seen Pali 3 paper. So I forgot to give context on Pali is a image text model, but that can generate text from our group and the extended group, like with colleagues across Google, which is basically image and text as input and then text as output again. So it can, and then trained in a multitask way. So it can do things like captioning images, but also answering questions about images, doing OCR on images. If the images are documents, it can answer questions about the documents or read some parts of the documents out and things like that. And the first two versions and papers of Pali, the image embedding model was always based on the best image embedding model we had at that time, which was always pre-trained in the classification way on the internal JFT data. This Pali model, each time, like the first one came out and then it was state of the art across a lot of these image text combined tasks. And then the second one called Pali X came out, where it's essentially same story, but more tasks, more benchmarks, and especially scaled up significantly the image and the text model. And then again, better across the board. And on the other hand, there's some other labs some other labs also had image text models based on clip encoder, I think, mostly for the image model. And then, but they were worse compared to Pali. So it may have given the impression that, yeah, even for these image text models, pre-training in classification way on large private data set like JFT may just be better. But there was never explicit comparison anywhere, just implicit by comparing, let's say, Pali to another existing model, like, let's say, Florence from Microsoft. But I'm just thinking of a random one. But there are many, many things that changes across these models, so you cannot really make such conclusion. So for Pali 3, we then basically did exact apples to apples comparison to figure out. So we compared across different scales, Siglib pre-trained image encoder, like plug this into Pali model. Pali model is image encoder, and then text encoder, and then text decoder. So for example, image encoder and T5 encoder decoder, and then concat the embedded image tokens with the text tokens, send it through the T5 encoder, and then T5 decoder generates answer. That was the first one. The next version said UL2 text encoder decoder instead of T5, but it's just a better one, and that's it. And basically what we found is that for almost across the board, it's better to use the Siglib pre-trained image encoder, except for linear classification probes, which is an important metric that many people, including ourselves, often use to judge model quality, which means take the image embedding, take the image model, embed a bunch of images, get the representations, and then do few-shot classification with that, with just a linear head. Or they are sometimes called linear probes, I think. And this across 8 different tasks. The classification pre-trained model was always significantly better across those. Yeah, so just to say, like, if you plug the model into a broader model and do more tasks than just classification, the result may be very different. And for example, Siglib may be much better, which is the case here. Then I think this is the last. Okay, yeah. Let's see about the time. 10 minutes. Okay. So one thing, there was a question earlier about this. What about hard negative mining and so on? We did a little investigation of this. I would say it's a preliminary indicator in the Siglib paper. So what if we can in some way get more difficult negatives into the mini batch? Would this be helpful? Is kind of the question. With Siglib, where each entry in this final loss matrix is independent of the rest, we can relatively easily do some experiment to check this hypothesis if it would be helpful to have more hard negatives by taking this big matrix, but computing the loss only on a subset of the examples. Like For example, okay, let's see. Um, this point here is the score we get with the regular cyclic training in some setting that we fix. Then this point here, the blue one, is the one I get if same training setting, but now in the loss matrix, I mask out the random half of them. So, right, we go through the same number of image text pairs or of training examples, but only for half of the pair combinations, we actually get a loss. Then we get this blue point. And then this is like 1/16th, and then 160th, and so on and so on. So we get worse and worse. This is a baseline. This is not interesting in itself. Now, what if we keep only the hardest half, right? We mask out the easiest half. So the half with the lowest loss, or which are already most similar. We just mask them out and don't put the loss on that. Then we get this orange line. This is like basically what if we could train with half the batch size, but they are all harder ones. So this is definitely better than the random masking, right? You need to compare this orange point with the blue point. And now, but we have, in principle, we have only seen half the number of pairs. Keep in mind, in this case, there is two things. There is the number of examples seen, which as you just iterate through the training, let's say a batch is 32,000. Then after one batch, you have seen 32,000 examples, but you have seen 32,000 to the square pairs, like image and text combinations, right? Because in one batch, you get the loss on all pairs. So there is two distinct things. And so while here we did equally many steps with the same batch size, so we have seen equally many examples as this point. We have only gotten loss on, meaning seen, half the amount of pairs. So you could say maybe that's why it didn't actually improve the results. So what if we match the number of pairs seen? And that is the pink curve. So the pink curve has trained double the steps as the orange and blue ones, but in each step, half the easier half of the examples in the mini batch being masked out. So the pink curve kind of shows you what if you could fill your batch only with harder examples. And that's what you get. So that would improve things a little bit. However, how to fill your batch with harder examples only without it being more expensive than random examples, we don't know. And we don't have any solution in this paper. So that is the situation with hard examples. Now, just very quickly, two more things, and then I want to leave at least time for a couple questions. One is that across different types of artificial noise we introduce, Sigmoid seems to be always more robust to noise. And this is consistent with we had a previous paper where in classification, we replaced Softmax with Sigmoid loss and found the same. It was more robust to noise. Yeah, let's forget about this one, but maybe this one can be useful in general. We just also put it in a paper. It's not really related to Siglip, but if you have a loss that looks like this, spiky, 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 but doesn't really die, and you're using Adam, this can be fixed in most cases, not all, by reducing Adam's beta 2 from 999 to 95, and then you get something like the green curve, which is much nicer. And I think I'll stop here. And yeah, you can find stuff on Colab, and maybe we can have the last 5 minutes for questions, if there are any. In the chat, what are next directions you're most interested in? Well, one thing is the Pali tree that I mentioned. When we plug this into a more general model that does all kinds of things, it's interesting. Also, what I mentioned a couple of times, I'm really interested in making as good as possible multilingual / multicultural model, and I think we only scratched the surface with this random collab that we made. So I'm quite interested in that. No more other questions? Right, people need time to write. You can also, if you want, just lift the hand and unmute and ask, right? There was another question. Also, if you have a second, can you talk about the captioning paper? Yeah, I guess if there is no other question. So there is one issue with all contrastive models, including Siglib. Um, why is Sigmoid more robust than Softmax? We only have a vague intuition, but don't really know why. Um, Yeah, remember what I described here about with the example with dogs and breeds. There is actually simpler example with relationships. Let's say I have the image of in the text of a cat sitting left of a dog in the mini batch, and no other images of cats or dogs in the mini batch, right? And no other texts of containing cat or dog. Then the model to solve the loss doesn't actually need to understand in detail that a cat is sitting left of a dog. It just needs to check um, there's a cat, and this text says something about cat. Yeah, that's the matching pair. That's good. And otherwise not, right? It doesn't need to understand the left of. And it would need to understand the left of if you had the exact opposite happening equally amount of time and ideally even in the same mini batch. But this is just not realistic, even with insanely large batch size. So there is this bunch of things that, and there have been a few papers, research showing this and benchmarks that these contrastive models mostly behave like a bag of word-ish thing. Bag of word is a bit exaggerated, um, but so more like detecting individual things in the image and not necessarily their relationship among each other. Um, and this is just inherent in the loss how they are trained. And me and another few colleagues thought about this and how would we train a model that doesn't have this, and what would be the simplest possible way to train a model that doesn't have this, because we always like simple things that are scalable, and eventually converge it to a captioning model should nail this or should be able to learn this. So it really is, for each image, generate the caption that belongs to it. Because then it needs to generate each token in the text, like to give each token in the text higher probability than anything else possible. Like then for this example of a cat sitting left of a dog, it needs to give left higher probability than everything else, including right. So eventually it needs to learn these kind of things. And we wrote a paper about this, which was called something like Image Captioners are Scalable Vision Learners too, or something like that. The model we call CAPPA, CAPPA, because it's a captioner, but we also had some twist on it with parallel decoder. But it doesn't matter too much. What matters is it's a captioner model. Um, yeah, there actually, to the question before of what I'm most interested in is also to push this captioner model pre-training much further. The question, maybe let's say the last one from the chat, if every image text pair is independent in loss, why does a very big batch size still help so well, except for accumulating the loss across devices and adding it at the end? Yeah, the thing I tried, I hopefully explained well the difference between example scene and pair scene, right? If you do 5 steps or 10 steps with batch size 32,000, you will see 32,000 square times 10 pairs, combinations that you learn about. Whereas if you do the 10 steps with batch, or, okay, if you go through I cannot make up the numbers on the spot. If you go through the same number of examples, the number of pairs you go through is different depending on the batch size. And with the larger batch size, because the number of pairs generated is square of the batch size, you still go through this much higher number of pairs with larger batch size. So that's the reason why large enough batch size still helps. This was a little bit difficult for me to explain. I hope I did a reasonable job. Okay, and I do need to go.
Yeah, I think we can end the session. Thank you so much for the talk.
Thank you for having me. Bye bye.